Let's go over test 2 review. Test 2 covers many different proof techniques, and we will practice them here. The first one, prove if x and y are odd integers, then x minus y is even. This will be a direct proof. So let's assume x and y are odd integers. Well, we need to use the definition. So we have two integers, say a and b, with x is 2a plus 1 and y is 2b plus 1. Now we just want x minus y. This is 2a plus 1 minus 2b plus 1, which you see is 2a minus 2b. We have 1 minus 1 adds to 0, and look, we can factor out a 2. So we get this as 2 times a minus b. Now, this is even as this a minus b is an integer. And this is the end of this proof. Number 2, a and b are integers. Then if 3 divides a and 5 divides b, then 15 divides the product, a times b. This again, direct proof. So we suppose we have integers with 3 divides a and 5 divides b. And we want to show 15 divides a times b. Well, we need to use the definition of divides. Let's see, I guess I'll call them x and y this time. We have x, y integers with, well, 3 divides a says 3x is a, and 5 divides b says 5y is b. Well, what do we see? If we multiply, we have that AB is 3x times 5y, and this is 15 times xy. Okay, well, we have this. We just need to make one final sentence. As xy is an integer, we see that 15 divides this product, a times b. This is the end of number 2. Number 3, this is an if and only if proof. You see, if I call this P and this Q, we are trying to prove P if and only if Q. Now, we know if and only if proofs have 2 directions. And so first, let's prove this direction, which would be P implies Q. We will do this direction directly. So let's assume N and Z is even. Okay, definition of even, there exists some integer x with n equals 2x. Now I want 7n plus 4 even, which means 2 times some integer. 7n plus 4 is 7, 2x plus 4, and this is 14x plus 4, which is 2 times 7x plus 2. You see, this is even, as 7x plus 2 is an integer. This completes the forward direction. Now you see we need to prove this way. Q implies P. We could assume 7n plus 4 is even, show n is even, but I think it's a little easier to do this direction using contrapositive. So this direction I will do contrapositive. Remember, I'm trying to show Q implies P. The contrapositive of that statement would be not P, implies not q. So we assume n is an odd integer, and we want to show that 7n plus 4 is odd. Well, we use the definition of odd. There exists, say, y and z with n equals 2y plus 1. Now I need to get 7n plus 4 as 2 times an integer plus 1. This is 7, 2y plus 1 plus 4, which is 14y plus 7 plus 4. You see, this is 14y plus 11, but I'll write this as 14y plus 10, and there's my plus 1. Then I can factor out a 2 from the first two terms. I get 7y plus 5 plus 1. We have an odd integer. So I just need to state this in a sentence. This is odd because 7y plus 5 is an integer. And this completes the proof. We have proven the forward direction directly, and then we proved this direction using contrapositive. So we can put our box at the end. Now we move into more contrapositive. We just had a taste of contrapositive in one direction of the if and only if proof, but now let's study this a little more with number 4. Suppose we have an implication. What's the difference between a direct proof and a proof by contrapositive? Well, we can explain just by talking about what we assume and what we show. In a direct proof, we assume P is true, and we need to show Q is true. Now, in a proof by contrapositive, we assume not Q is true, and then we show not P is true. And in effect, in a proof by contrapositive, we have proved the contrapositive, but we know this is logically equivalent to the implication. Now we move on to part B. We want to give a proof by contrapositive of the following. Okay, let me underline some things. Okay, this is our P and this is our Q. So we're adding 3 consecutive integers. The statement is if the sum of 3 consecutive integers is odd, then the smallest of the 3 consecutive integers is even. Let's begin our proof, but we need to state that we're doing this by contrapositive. That way the reader knows what we're doing. So we will prove by contrapositive. Okay, so let's assume the smallest of 3 consecutive integers is odd. So that would be that x and z is odd. Now this will be the smallest of my 3 consecutive integers. That means, well, we want to show, let's take x, then the next one, x plus 1, and then the next one, x plus 2. This will be even, okay? This is exactly what I want, right? This part is the sum of the 3 consecutive integers with this being the smallest. And so we have written what we assume, proving by contrapositive, and what we need to show. Wonderful. Well, as x is odd, there exists, say, n and z with x equals 2n plus 1. If we take x plus 1 plus x plus 2, this is 2n plus 1 plus 2n plus 2, and then plus 2n plus 3. this we want to show is even. Well, we have altogether 6n, and then we have plus 6. Okay, this definitely looks even. We just factor out a 2, and then we have n plus 3. This is even as n plus 3 is an integer. And this completes the end of this proof. Number 5, for x, y, z natural numbers, we will prove the following. If xy is z squared, then x is less than or equal to z, or y is less than or equal to z. This is an implication. I can label this p and this q. Then we have p implies q. You notice q is an or. I find this easier to, let's see, contrapositive, because I will use De Morgan's, where if you negate, let's see, I don't want to call them P and Q, but maybe let's do an S or T. This is logically equivalent to not S and not T, which means here, if I assume not Q, as I will in a proof by contrapositive, I have a lot to assume. I will assume not this, and I will assume not this one. So let's begin exactly as I just said. We will prove this by contrapositive. We assume, well, we have x, y, z natural numbers. And then this not Q is that x is bigger than z and y is bigger than z. Okay, and I want to show, well, not P, which is that xy is not equal to z squared. This is exactly not Q implies not P. Well, x, y, z are natural numbers, meaning they are positive. When you multiply a inequality on each side by a positive number, it does not switch the way the inequality goes. So let's use this now. As x is bigger than z and y is positive, we have that xy is bigger than zy. And we can do this again. As y is bigger than z and z is positive, we have, let's say, zy is bigger than z times z. Okay, so now what do we do? Well, you see, we have xy is bigger than z squared. In particular, it is not equal to z squared. Thus, xy is bigger than z squared. And this is exactly what we wanted to show, not equal to. This is the end. We have proved this statement using contrapositive. Now, contradiction. Prove there is no smallest even integer. How can we do this? Well, we know in a proof by contradiction of a statement, say, S, we assume not S is true, and then we argue until we reach something that's always false. So let's do this here by contradiction. We assume there is a smallest even integer. And we can just say, call it A. So A is now the smallest even integer. Well, definition of even, there exists n and z with A equals 2n. Now, what I need to do, what can I contradict here? I can contradict the following, this word, smallest. So I want to create an even integer that is smaller than A. And how can I do this? Well, consider y, which is 2n minus 2. Clearly, y is less than a, and also y is an integer. Moreover, we can write y as follows. It's 2 times n minus 1, which is even, as n minus 1 is an integer. And so this contradicts that a is the smallest even integer. And this completes the proof. What I contradicted is here, smallest, as I mentioned I would. This completes the proof. There is no smallest even integer. Number 7, we are trying to disprove. And to disprove a statement like this, we need a justified counterexample. Well, let's look at the statement. It says the following: A, B, C are integers. If A divides C and B divides C, then the sum, A plus B, also divides C. Okay, this is definitely not true, but we need to justify. So let's consider 2, 3, and 6, which are definitely integers. Then we see 2 divides 6 and 3 divides 6, but 2 plus 3 is 5, and 5 does not divide 6. And so this is a counterexample, because just as a comment, a counterexample would be, you see this is an implication, it would be an example where this part is true and this is false. This is the only time an implication is false, is when you have a T followed by an F. And that's what we have justified. You see, 2 divides 6 and 3 divides 6, but 5 does not divide 6. Okay, now let's move into some set theoretic proofs. We have, but this first one also has to do with divides. So for an integer a, we define this sets capital A and capital B. Capital A is all integers x, such that x divides a. Capital B is all integers x, such that x divides a squared. And the first part, we want to prove that capital A is a subset of capital B. How do we prove subset? Well, you just let x be an element of A, and we need to show x is an element of B. Because remember, this here is an implication. The meaning of this is as follows. This means that x in A implies x in B. That's the meaning of A is a subset of B. And so we have to show this implication. Okay, what does it mean to be an element of A? It says there exists some n and z with x divides A. So xn equals A. Now I want x divides A squared. Let's just multiply both sides by A. And I can put parentheses like this. NA is an integer. We see that x divides A squared, meaning that this little x is an element of B. So we have proven part A. This is the end of part A. Letter B. Well, we're given a specific value of A here. So for A equals 10, capital A is all integers x, such that x divides 10. And capital B is all integers x, such that x divides 100. The question is, does A equal B? In this case, we must justify our answer. I will just say, in this case, A is not equal to B. Now, let's think about how we could justify this. So let's think Venn diagrams for a moment. We have shown A is a subset of B. So maybe A is here, and then B is, say, here, right? Here's B. Okay, so we have shown it looks something like this. So to justify A is not equal to B, we need to find one element. Maybe I'll make it pink here. That is in B, but not in A. And then we will have justified what I mentioned was true, that A is not equal to B. Let's see, 50 is in B, as 50 divides 100, but 50 is not in A, as 50 does not divide 10. And this would be the justification as to why A is not equal to B. Similarly, 100 is in B, and 100 is not in A. But we just need one example of an element in B that is not in A. Number 9, for sets A and B, we want to give a set theoretic proof of the following. If A union B is A, then A intersect B equals B. Now, I outline this part on purpose. Set theoretic proof. This means not a Venn diagram. This means using sentences. This means showing two sets are equal with a proof. Okay, so do not just draw a Venn diagram and write done or something like this. That is not a set theoretic proof. Okay, you can draw a Venn diagram to visualize, but then make sure you follow it with a set theoretic proof when you are asked here. This is an important part. Okay, well, we assume we have sets A and B, and A union B equals A. And then we show that A intersect B equals B. Now, we know how to show set equality, right? There are two parts. First, we must show subset in this direction, namely that A intersect B is a subset of B. Then we must show subset in this direction, that B is a subset of A intersect B. One direction is very clear. I will still write it just for the completeness of this proof. Let's let X be an element of A intersect B. We need to show X is an element of B. Well, this is quite short. X is an element of A intersect B means that X is in A and X is in B. And, well, in particular, X is in B. So this direction is finished. Like I said, I was just including this direction for completeness. Now for the other direction, let's let X be an element of B and show X is an element of A intersect B. And once we do, then we're finished with this problem. Well, X is an element of B. We see certainly X is in A or X is in B is true. And this means X is in A union B. Now, here comes our hypothesis for the first time in this proof. A union B equals A. As A union B equals A, we have X is in A. Okay, so now let's put together everything. X is in A and X is in B, right? Because X is in B and we have just shown X is in A. And so X is in the intersection. And this completes this direction. This is what I wanted to show. And Since we have proved subset are equal to in each direction, this is the end of this proof. Now, contradiction. We want to prove B minus A intersect A is empty. How do you prove a set is empty using contradiction? Well, you just assume it's not empty. Argue until you reach a contradiction. We assume we have some x in B minus A intersect A. Now, what does this mean? Well, x is in this set B minus A, and x is in A. We can unravel one more time. This part here, it means that x is in B and x is not in A. And you see we have reached our contradiction. It's always good to write what your contradiction is so that your reader is very clear that you're finished. We have a contradiction, namely, x is in a set and at the same time it is not in a set, the same set A. This is our contradiction. And this is the end of this proof. Number 11. Well, this problem involves Fibonacci numbers, but it's the first of a few that are induction problems. Let's remind ourselves about the Fibonacci numbers. Well, they satisfy F1 is 1, F2 is 1, and then you get the nth Fibonacci number by adding the two that came before. So for example, we can write out a few Fibonacci numbers. It goes 1, 1, then we add 2, then we add 3, then we add, and, well, we add. Okay, so this is out to F8, for example. But now let's get into the specific problem. We want to prove if we add from I equals 1 to n of F2i that we get F2n plus 1 minus 1. And we will do this by induction. A proof by induction has two parts. We have a basis step. Usually the basis step is a verification. And then we have an inductive step. Our basis step, well, this is n equals 1. And the left-hand side, this is just a sum of one term. This is just F2, which we know is 1. The right-hand side, well, when n equals 1, this would be F3 minus 1. And you see we've calculated a few Fibonacci numbers in pink above. F3 is 2. And 2 minus 1 is 1. So you see both the left-hand side and the right-hand side are equal to 1. We have finished the basis step. Now for the inductive step. We assume k is a natural number with, well, if we add I equals 1 to k of F2i, we get F2k plus 1 and then minus 1. And we want to show, well, that this holds for k plus 1. And this would be if you add I equals 1 to k plus 1 of F2i, we get, well, the right-hand side for k plus 1 would be F2. It would be here. This would be 2k plus 2 plus 1, which is 2k plus 3 minus 1. This is what we want to show. So let's just start with the left-hand side. We have this sum. What I want to do is, of course, use my inductive hypothesis. And so I will write this as a sum of the first k terms and then the k plus first term. And when I evaluate this at k plus 1, I get F2k plus 2. Now, here comes my inductive hypothesis. This is equal to f2k plus 1 minus 1 plus f2k plus 2. This is where I used that. It is precisely writing this equal to this, okay? Well, so far I haven't used that these are actually Fibonacci numbers, and this is where I will use that. We know f2k plus 1 plus f2k plus 2, the sum of any two consecutive Fibonacci numbers is the next one. So this will be f2k plus 3 minus 1. And perfect. You see, this is exactly what I wanted. And so I just write that as desired. And this is the end of our proof by induction. Number 12. Well, we want to prove if you add from 0 to n of I times I factorial, we get n plus 1 factorial minus 1. Just as a comment, you could very easily start this sum at 1 because 0 times 0 factorial is 0 times 1, which is 0. So the 0th term in this sum is 0 anyways, but it's also correct as written. Okay, well again, this is by induction. We have a basis step and we have an inductive step. The basis step we are trying to prove for natural numbers, so we begin with n equals 1. The left-hand side, as I was saying, is 0 times 0 factorial plus 1 times 1 factorial. But this part is 0, so we get 1 times 1 factorial, we get 1. And the right-hand side, well, this would be 2 factorial minus 1. 2 factorial is 2, so we get 2 minus 1, which is 1. We have the left-hand side equals the right-hand side. They are both 1, and so our basis step is complete. Now for the inductive step. We assume we have k, a natural number, with, well, if we add I equals 0 to k of I times I factorial, we get, this would be k plus 1 factorial minus 1. And then we want to show if we add to k plus 1 of I times I factorial, this would be, well, this would be k plus 2 factorial minus 1. Again, we start with the left-hand side. So we have, if we add and then the k plus first term would be k plus 1 times k plus 1 factorial. This is not the inductive hypothesis, not yet. I just wrote the sum from 0 to k and then plus the I equals k plus 1 term here, okay? Now, here comes the inductive hypothesis. We have this is equal to k plus 1 factorial minus 1 and then plus this term just remains the same. This was using the inductive hypothesis. It was going from here to here. Okay, now we need to do some algebra. Well, if you look, this term and this term both have k plus 1 factorial, so I can factor this out of these two terms. So I have k plus 1 factorial. When I do, well, here, if I factor out a k plus 1 factorial, I'm just left with 1. And then here, I have just this, k plus 1. Now, I still have this minus 1. So let me do one more step, and then we're almost finished. This is k plus 2 times k plus 1 factorial, we have -1. And now if you look at this, we realize we're done, almost, because k plus 2 times k plus 1 factorial is exactly k plus 2 factorial. So this is k plus 2 factorial minus 1. And this is exactly what we were trying to prove. So we are finished with this proof by induction. Number 13, we have an, this is a sequence, and this is defined recursively, right? Because a1 is the square root of 2, and an, to get the nth term, you take the square root of 2 times an minus 1. Now, we're not trying to prove an explicit formula for this recursively defined sequence. We are trying to prove that an sits between 1 and 2, strictly between. And we will do this by induction. In our basis step, this is verification. We're trying to prove this for natural numbers, so our basis step involves n equals 1. Well, for n equals 1, a1 is the square root of 2. And, well, certainly, the square root of 2, it sits between 1 and 2. And this is all we need to show for the basis step. Now for the inductive step. We assume we have some natural number k, and 1 is less than ak is less than 2. We want to show, well, show for k plus 1 that 1 is less than ak plus 1 is less than 2. Well, there's really two things to show. First of all, ak plus 1 is bigger than 1, and second of all, ak plus 1 is less than 2. So we have, well, we use this, that ak plus 1 equals, it's 2 times ak. Now, this is bigger than, because you see ak is bigger than 1, so this is bigger than the square root of 2 times 1. And the square root of 2 is bigger than 1. Okay, so that's one side. Similarly, I can just recopy this, that ak plus 1 equals 2 times ak. Now, ak is less than 2, so I can replace, this would be less than 2 times 2, which is the square root of 2, square root of 4, and this equals 2. So we have shown 1 is less than ak plus 1 is less than 2. This is exactly what we were trying to prove. And this is the end of this proof by induction. This is also the end of test 2 review. Thank you very much.